You're lying in bed, maybe on your phone, maybe on a laptop, and you tap a link, something you've done thousands of times. The page loads. You start reading. But right now, I want you to think about that moment between the tap and the page. That tiny gap where the screen goes blank, or a loading bar flickers, or nothing visible happens at all. Because that gap is not empty. It's full. It's one of the most complicated things happening anywhere on the planet. And it happens so fast and so reliably that you've probably never once stopped to wonder what's going on inside it. So tonight, we're going to slow that moment way down. We're going to follow your tap, your click, whatever you want to call it, all the way down through the layers of the machine, past the software, past the operating system, past the code, down into the physical switches and the electrical signals. And then we're going to come back up through every layer until the page appears on your screen. 6 layers down, 6 layers back up. And by the time we reach the bottom, you'll start to see why that ordinary little moment is one of the stranger engineering accidents in modern history. Nobody designed this system from the top down. Nobody sat in a room and planned out how a click would become a web page. What actually happened is that people solved problems, one at a time, over the better part of a century, and the solutions stacked on top of each other in ways that nobody fully predicted. Each layer was built to solve a problem that the layer below it created. And what you get when you zoom out is this strange, beautiful tower of translations, where each level speaks its own language, and each level has no idea what the levels above or below it are really doing. That's what we're going to walk through. Slowly, the way you'd explain it to someone sitting next to you who's curious but comfortable and not in any hurry to get anywhere. I should warn you, by the way, that some of this is genuinely surprising. Not in a flashy way, but in a quiet way. The kind of surprise where you learn how something works and then you can't stop noticing it. Let's start at the surface, with the thing you can actually see. You tapped a link. That means your finger, or your mouse cursor, or your trackpad made contact with a specific point on your screen. And your screen is actually a grid. Every point on that screen has a position, a pair of coordinates, and when you touch it, the hardware underneath the glass detects exactly where the contact happened. On a touch screen, this works through capacitance. Your finger is slightly conductive, so when it gets close to the screen, it changes the electrical field at that spot. The screen's controller chip notices the change, figures out the coordinates, and sends that information to the operating system as an event. On a laptop with a trackpad, the idea is similar. The trackpad detects the position of your finger, translates it into cursor coordinates, and when you click, it sends that click event along with the cursor's position. So now the operating system has received a message. Something like, a click happened at these coordinates. The operating system doesn't care what's at those coordinates. All it does is figure out which program owns that part of the screen and pass the message along. In this case, the program is your web browser. The browser gets the click event, checks the coordinates, and realizes that they land on a link, a specific piece of text that has a web address attached to it, an address that points somewhere else on the internet. And this is the moment where things start to get interesting, because the browser now has a job. It needs to go and get the page that the link points to. But the address is just a name, something like a website's domain followed by a path. It's readable by humans, which is the whole point, But the internet doesn't run on human-readable names. The internet runs on numbers. Every computer connected to the internet has a numerical address. And to reach the right one, the browser needs to translate the human-readable name into that numerical address. This translation has a name. It's called a DNS lookup, and the system that handles it is called the domain name system. Think of it as a massive, distributed phone book. Your browser sends the name to a DNS server, and the DNS server sends back the number. Now the browser knows exactly which computer on the internet to contact. But sending a message to another computer isn't as simple as just shouting into the void. There's a protocol, a set of rules that both sides have agreed to follow. Before any data gets exchanged, the two computers need to establish a connection. They do a kind of handshake, a back and forth, where each one confirms it can hear the other, and they agree on how they'll communicate. Once that's done, the browser sends its request. The request says, essentially, please send me the contents of this page. And the server, the other computer, receives that request, finds the right file, and sends it back. What comes back is text, just text. It's written in a language called HTML, which stands for Hypertext Markup Language, and it's a set of instructions that describe the structure of the page, where the headings are, where the paragraphs go, which words are links, what images to include and where to put them. If you've never seen raw HTML before, it doesn't look like a web page at all. It looks more like a recipe, a list of ingredients and steps, with little labels wrapped around each piece of content. The browser reads those labels and knows what to do with them. A human reading the raw file would see a mess of angle brackets and tag names, but the browser sees structure. And that's what the browser does next. It reads the HTML piece by piece and starts constructing the page in memory. It figures out the layout, applies the colors and fonts, loads the images, calculates where everything goes, and then paints the final result onto your screen, pixel by pixel, row by row, until the page you tapped on appears exactly the way its designer intended. All of that, from your tap to the finished page, happens so fast that you probably wouldn't even notice there were steps involved. You'd just see a page appear and start reading. Most people do. Most people have been doing exactly that for decades and have never had a reason to wonder what's going on behind the screen, which is fine. That's the whole point of good engineering. It disappears. It does its job so well that you forget there's a job being done at all. But here's what makes this worth spending the next 2 hours on. Every single step I just described, every one of them, is hiding an enormous amount of work underneath it. When I said the screen detects your finger, I skipped over how electrical signals get turned into numbers. When I said the browser sends a request, I skipped over how a message travels across an ocean through a cable on the seafloor. When I said the CPU reads the HTML, I skipped over what reading even means for a machine that doesn't understand language or meaning at all. Every layer is a surface, and underneath every surface is another layer with its own logic, its own history, and its own set of problems that somebody had to solve. We're going to go through all of them. We'll start right here at the browser and work our way down, one layer at a time, until we reach the actual physics, the electrical signals moving through switches, and then we'll come back up. The first question, the one that pulls us into the next layer, is deceptively simple. The browser received your click and figured out it was on a link. The link had a web address attached to it. That address is stored somewhere inside the computer as data. But what does data actually look like inside a machine? Not on the screen, where it's letters and numbers you can read, but inside, where there's no screen, no human language, no alphabet. What is information made of when there's nobody looking at it? The answer, it turns out, is almost disappointingly simple. Inside your computer, every piece of information, every letter, every number, every image, every sound, every line of code, everything is made of the same two signals. On and off. High voltage and low voltage. You can call them 1 and 0 if you like. And most people do, but really they're just two states. A wire either has a charge running through it, or it doesn't. A tiny spot in memory is either holding a voltage, or it isn't. That's all there is. Two options, repeated over and over, billions of times across billions of tiny locations inside the machine. Now I realize that sounds absurd. Two signals don't feel like enough to build anything interesting, let alone an entire web page with text and images and colors and links. But this is one of those cases where the math works even when the intuition doesn't. One switch by itself is almost useless. It can say yes or no, on or off, true or false. That's one bit of information, and it's not worth much on its own. But the moment you start putting switches together, the number of things you can say grows fast. Two switches can be in 4 possible combinations. 3 switches can be in 8. 4 can be in 16. By the time you get to 8 switches, you have 256 possible combinations. And 256 turns out to be a very useful number. 8 switches grouped together is what we call a byte. And a byte can represent 256 different values, which is enough to cover every letter of the English alphabet, both uppercase and lowercase, plus every digit, plus all the common punctuation marks, and still have room left over. This is exactly what a system called ASCII does. ASCII stands for American Standard Code for Information Interchange, and it was published in 1963. It's essentially a lookup table. It assigns a specific number to every character. The capital letter A is number 65. The lowercase letter A is number 97. The digit 0, the character, not the number, is 48, and so on. So when your computer needs to store the word hello, it doesn't store the word in any human sense. It stores 5 numbers, 1 for each letter, and each of those numbers is stored as a pattern of on and off signals in 8 switches. The computer doesn't know what those patterns mean. It doesn't know that 65 is supposed to be the letter A. That meaning only exists because there's a program reading those patterns and translating them back into characters based on the same agreed-upon table. ASCII worked well for English, but the world has a lot more than one alphabet. There's Chinese, Arabic, Hindi, Korean, Japanese, Greek, Cyrillic, and dozens more. ASCII's 256 values couldn't begin to cover all of them. So over time, the computing world adopted a much larger system called Unicode. Unicode works on the same principle, a number assigned to every character, but it uses more bits per character, so it can cover tens of thousands of symbols across every modern writing system. The key idea stayed the same. Numbers, all of them. Patterns of on and off signals. The only difference is that the lookup table got bigger. Numbers themselves work the same way. You and I count in base 10 with 10 digits, 0 through 9. When you run out of digits in the ones column, you carry over to the tens column, then the hundreds, and so on. Binary, base 2, works exactly the same way, except there are only 2 digits, 0 and 1. So you count 0, 1, and then you've already run out of digits. The next number, 2, gets written as 10. 3 is 11. 4 is 100. The number 42, if you're curious, is 101010 in binary. It looks strange on paper, but the math is identical to what you already know. The rules are the same. The digits are just fewer. And here's a small historical note that I think is interesting. The binary number system wasn't invented for computers. The German mathematician Gottfried Leibniz described it formally all the way back in the late 1600s, more than 2 centuries before anyone built an electronic computer. He was interested in it as a mathematical curiosity. The idea that you could represent any quantity using only 2 symbols sat around for a very long time before anyone realized it was the perfect language for a machine built out of electrical switches. What about images? An image on your screen is a grid of tiny dots called pixels. Each pixel has a color, and that color is stored as 3 numbers. 1 for how much red, 1 for how much green, and 1 for how much blue. Mix those 3 values in different amounts, and you get every color the screen can show. A pixel that's pure red might be stored as the values 255 for red, 0 for green, 0 for blue. A pixel that's white has all 3 values at 255. A pixel that's black has all 3 at 0. A rich purple might be high red, 0 green, high blue. You get the idea. Every image you've ever seen on a screen, every photo, every video frame, every icon is just a grid of these 3 number sets. And each number is stored as a pattern of bits. A typical photo on your phone might be several million pixels, each one defined by 3 color values, each value stored as 8 bits. That adds up to tens of millions of bits for a single image, which sounds like a lot, and it is. But the machine doesn't care. It handles bits the same way, whether there are 100 of them or 100 million. It doesn't get tired, and it doesn't slow down because the numbers are bigger. It just processes them one at a time, very, very quickly. Sound works on a similar idea, though it's not a grid. A microphone converts sound waves into a constantly changing electrical signal. To store that signal digitally, the computer samples it, takes a measurement of the signal's level, thousands of times per second. Each measurement becomes a number. String all those numbers together in sequence, and you have a digital recording. Play them back through a speaker, converting the numbers back into a smoothly changing electrical signal. And you hear something very close to the original sound. It's not perfectly identical. There's always some fine detail lost in the sampling process. But if you take enough measurements per second, the human ear can't tell the difference. The music you stream, the voice notes you send, the sound effects in a game, all of them are just long sequences of numbers, stored as patterns of bits, interpreted by a program that knows how to turn them back into vibrations in a speaker cone. So we've got letters, numbers, images, and sound, and they're all stored the same way. Patterns of ones and zeros, patterns of on and off. The computer doesn't prefer any one type of data over another, because it doesn't actually know the difference. The same 8 bits that represent the letter A could just as easily represent the number 65, or a particular shade of very dark blue, or a tiny fraction of a sound sample. The meaning isn't in the bits. The meaning is in the program that reads them. The program knows what to expect, a text file, or a photograph, or a song, and it interprets the patterns accordingly. Change the program, and the same bits mean something entirely different. This is one of the quietly strange things about computers. There's no intelligence in the storage itself. The memory inside your machine holds billions of on-off states, and not a single one of them has any inherent meaning. The meaning is always somewhere else, in the software, in the agreements, in the standards that humans wrote down and that programs follow. The bits are just raw material. Everything interesting about a computer comes from what you do with them. And if you think about it, that's a remarkable design choice, even though nobody really made it as a single conscious decision. It means the same machine that displays your web page can also play music, edit a photograph, run a spreadsheet, or simulate the weather. The hardware doesn't change. The switches don't get swapped out. The only thing that changes is the software, the set of instructions that tells the machine how to interpret all those on-off patterns. This is why a computer is different from, say, a calculator or a clock. A calculator can only do arithmetic. A clock can only tell time. But a computer, because its storage is general and its meaning is imposed by software, can do anything that can be described as a sequence of simple operations on binary values, which, it turns out, is almost everything. And that raises a question that might have been bothering you since the beginning of this section. We've been talking about ones and zeros, about on and off, about voltages being high or low. But what actually does the switching? What's the physical thing inside the computer that holds a voltage or doesn't, that represents one bit of information? What are these switches made of? And how do you fit billions of them into a chip you could balance on the tip of your finger? The switch is called a transistor, and it is one of the simplest devices ever invented. It has 3 connections. Apply a small voltage to one of them, and current flows between the other 2. Remove that voltage, and the current stops. That's it. On or off, controlled by a signal. No moving parts, no gears, no springs, nothing mechanical at all. Just a tiny piece of semiconductor material, usually silicon, arranged so that a small electrical nudge controls a larger electrical flow. You can think of it like a faucet, except the handle is made of electricity, and the water is also electricity. The transistor didn't always exist, of course, and the machines that came before it used something much clumsier. Before transistors, the switches inside computing machines were vacuum tubes, glass cylinders about the size of your thumb, sometimes bigger, that worked on a completely different principle. They did the same basic job, controlling the flow of current, but they were hot. They burned out regularly. They consumed enormous amounts of power. And they were big enough that building a machine with thousands of them meant filling an entire room and generating so much heat that you needed industrial cooling just to keep the thing running. In December of 1947, at Bell Telephone Laboratories in New Jersey, 2 physicists named John Bardeen and Walter Brattain demonstrated the first working transistor. It was a point-contact transistor, crude by modern standards. Basically, a tiny wedge of germanium with 2 gold contacts pressed against it. It wasn't much to look at, but it proved that a solid piece of material, with no vacuum, no heated filament, no glass envelope, could do the same job as a vacuum tube. Their colleague, William Shockley, went on to develop the junction transistor, a sturdier and more manufacturable design that became the foundation for everything that followed. All three shared the Nobel Prize in Physics for this work. The credit for the transistor's invention is sometimes simplified to just Shockley's name, but the actual story involves all three, and the relationships between them were complicated in ways that have filled entire books. What matters for our purposes is the result: a switch that was smaller, cooler, more reliable, faster, and cheaper than a vacuum tube. And crucially, a switch that could be made smaller and smaller over time. In the years after Bardeen and Bratton's demonstration, engineers figured out how to shrink transistors, first onto individual chips of silicon, then onto integrated circuits where many transistors shared a single piece of semiconductor. By 1971, the Intel 4004, the first commercially available single-chip microprocessor, packed 2,300 transistors onto a chip. Today, a modern processor contains billions of them. The number is almost absurd, but the principle hasn't changed. Each one is still just a switch, on or off. The only difference is how many you can fit in one place, and how fast they can flip. But there's a subtlety here that's worth mentioning before we move on. A transistor is an analog device. The voltages inside it aren't perfectly clean ones and zeros. They're messy, real-world electrical signals with noise and variation. What makes a computer digital is a design choice. The engineers agree on a threshold. Any voltage above a certain level counts as on, and anything below a different level counts as off. The grey area in between is ignored, treated as invalid. This is what MIT's introductory computing course calls the digital abstraction, and it's one of the most important ideas in the entire field. It means that the sloppy, imperfect real world of physics gets cleaned up into a neat binary world of logic, and the logic never has to worry about the physics again. Each layer trusts the layer below it to deliver clean signals. And there's a beautiful consequence of this. If noise creeps into a signal somewhere along the way, the next gate that reads it snaps the voltage back to a clean high or low before passing it along. The small errors get corrected at every stage instead of accumulating. This is why a computer can run for hours, processing trillions of signals, and never drift into nonsense. The digital abstraction cleans up after itself. Now, one transistor by itself is just a switch. It can be on, or it can be off. It stores or represents one bit. But the interesting things start happening when you connect transistors together in specific patterns. And this is where a man named Claude Shannon enters the story, though he enters it from the math side rather than the hardware side. In 1938, Shannon published his master's thesis at MIT, and in it, he proved something that turned out to be one of the most consequential ideas in the history of engineering. He showed that Boolean algebra, the branch of mathematics that deals with true and false, and or and not, maps directly onto electrical switching circuits. Every logical operation you can describe with Boolean algebra, you can build with physical switches. This meant that logic, abstract reasoning about true and false, could be performed by hardware, not by a person flipping switches, but by the circuit itself, automatically, as fast as electricity can flow. The basic building blocks that come out of this idea are called logic gates. A gate is a small arrangement of transistors that takes one or two input signals and produces one output signal, following a fixed rule. The simplest gate is the NOT gate, sometimes called an inverter. It takes one input. If the input is on, the output is off. If the input is off, the output is on. It flips the signal. You can build one with a single transistor. Then there's the AND gate. It takes two inputs and produces one output. The output is on only if both inputs are on. If either one is off, the output is off. Picture two switches in a row. Both have to be closed for current to flow through. The OR gate also takes two inputs, but its rule is different. The output is on if either input is on, or if both are on. The only way the output is off is if both inputs are off. Picture two switches side by side. Either one can let current through. These three, NOT, AND, and OR, are enough to build any logical operation. But there's a gate that's even more interesting, and it's called NAND, which stands for NOT AND. A NAND gate gives you the opposite of an AND gate. Its output is off only when both inputs are on. In every other case, the output is on. What makes NAND special, and this is one of those facts that sounds dry until you realize what it means, is that NAND is universal. You can build any other gate, AND, OR, NOT, anything, using nothing but NAND gates. MIT's introductory computing course teaches this as one of the foundational principles of digital design. In theory, you could construct an entire computer using only one type of gate. In practice, chip designers use a mix, but the universality of NAND is what guarantees that the whole system holds together logically. So now you have gates, and gates can evaluate logical statements. But can they do math? This is where it gets satisfying, because the answer is yes, and you can see exactly how it works with just two gates. Consider the simplest possible addition, adding two single-bit numbers together. Each number is either 0 or 1. There are four possible combinations: 0 plus 0, 0 plus 1, 1 plus 0, and 1 plus 1. And the first three are obvious. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. The only tricky case is 1 plus 1, which equals 2. But 2 in binary is 1, 0. That means the result has two parts: a sum digit, which is 0, and a carry digit, which is 1. It turns out there's a gate that produces exactly the right sum output. It's called an XOR gate, short for exclusive OR. XOR is on when the inputs are different, and off when they're the same. And the carry output is just an AND gate, which is on only when both inputs are on. Put those two gates together, an XOR for the sum and an AND for the carry, and you've built what's called a half adder. It can add two single-bit numbers and produce a two-bit result. Chain several of these together, with each carry feeding into the next stage, and you get a full adder that can add numbers of any size: 8-bit numbers, 16-bit numbers, however many bits you need. And this is the part that I think is genuinely worth pausing on, because it's easy to hear it and move on without noticing how strange it is. Nobody designed the transistor to do arithmetic. Bardeen and Bratton were trying to build a better amplifier for telephone signals. Shannon was writing a math thesis about switching circuits, not designing a calculator. The logic gates that emerged from their work weren't built with addition in mind. They were built to evaluate true or false statements. But because addition follows logical rules, and because gates can evaluate logical rules, the gates can add. The math doesn't care what the gates were designed for. The behavior emerges from the pattern, from the way the pieces connect, not from any cleverness in any single piece. A transistor is as simple as a light switch. A gate is just a handful of transistors. An adder is just a handful of gates. And yet, an adder can do something that feels, to a human watching it work, like thinking. If you're enjoying following this trail down through the layers of the machine, and you'd like more of these kinds of explanations, subscribing is the simplest way to make sure you don't miss the next one. But we've still got a problem. An adder can add two numbers. That's useful, but it's a long way from loading a web page. To get from here to a working computer, you need something that can follow instructions, a whole sequence of different operations, one after another, chosen from a list, executed in order. You need a machine that can read a command, figure out what it means, carry it out, and then move on to the next command. You need the thing at the center of every computer ever built. You need the CPU. And the question that opens the next layer is, how does a machine built entirely out of these tiny, simple, mindless switches manage to follow instructions? The CPU, the central processing unit, is the part of the computer that actually does things. Everything else we've talked about so far, the transistors, the gates, the adders, those are the building materials. The CPU is the structure built from them. And the strange thing about it, the thing that takes a while to really absorb, is that the CPU does not do very much. It does one small thing at a time, following a very simple routine, and it does it over and over again, incredibly fast. The routine has 3 steps: fetch an instruction, decode that instruction, execute it, then go back to the beginning and do it again with the next instruction. That's it. That loop, fetch, decode, execute, is the heartbeat of every computer ever made. Let's slow it down and walk through each step, because once you see how it works, you'll understand the core of the entire machine. The first step is fetch. Somewhere in the computer's memory, there's a list of instructions. They're stored as binary numbers, one after another, each one at a specific address. The CPU keeps track of where it is in this list, using something called the program counter. The program counter is just a register, a tiny piece of fast storage inside the CPU, and it holds the address of the next instruction. When the CPU is ready for a new instruction, it looks at the program counter, sends that address to memory, and memory sends back the instruction stored at that location. That's the fetch. The CPU now has a binary number sitting in another register, called the instruction register, and that number is the instruction it's about to carry out. The second step is decode. The instruction is just a pattern of bits, and the CPU needs to figure out what it means. Different patterns mean different things. Some bits specify what operation to perform: add, subtract, compare, copy, move data around. Other bits specify which registers to use, or where in memory to find the data. The part of the CPU that handles this is called the control unit. The control unit reads the instruction, breaks it apart, and sets up the internal wiring of the CPU so that the right operation will happen with the right inputs. You can think of the control unit as a dispatcher. It doesn't do the actual work. It reads the order and routes it to the right department. The third step is execute. The actual operation happens here. If the instruction says to add 2 numbers, the values get sent to the arithmetic logic unit, the ALU, which is the part of the CPU built from the kinds of adder circuits we talked about in the last section. The ALU performs the addition and puts the result in a register. If the instruction says to load a value from memory, the CPU sends the address to memory and waits for the value to come back. If the instruction says to compare 2 numbers, the ALU subtracts one from the other and sets a flag indicating whether the result was 0, positive, or negative, so a later instruction can make a decision based on the outcome. Once the execute step is done, the program counter advances to the address of the next instruction, and the whole cycle starts again. Fetch the next instruction, decode it, execute it, advance, repeat. There's something almost meditative about the simplicity of this loop when you sit with it for a moment. The CPU doesn't stop to think about what it just did. It doesn't remember the context of the previous instruction in any meaningful way. It doesn't have a goal or a plan. It just moves on. The only thing connecting one instruction to the next is the data they leave behind in registers and memory, and the program counter telling the CPU where to look next. Every complex behavior you've ever seen a computer perform, loading a web page, playing a video, auto-correcting your text, is ultimately this loop running millions or billions of times. Each iteration doing one small, almost trivially simple thing. Now, all of this is synchronized by a clock. The clock is a tiny crystal oscillator that sends out a regular electrical pulse, a tick at a fixed rate. A modern processor might tick several billion times per second. The clock doesn't do any computing. It just keeps everything in step. Each stage of that 3-step cycle is coordinated with the clock's ticks, so that signals have time to propagate through the circuits and settle into stable values before the next stage begins. Without the clock, the various parts of the CPU would get out of sync with each other and produce garbage. The clock is the metronome that keeps the whole orchestra playing together. I should mention that the relationship between clock ticks and instructions isn't as simple as 1 tick per step. Modern processors use a technique called pipelining, where those 3 stages overlap. While one instruction is being executed, the next one is already being decoded, and the one after that is already being fetched. Intel's educational materials describe this as a way to increase throughput without making any individual stage faster. It's like an assembly line. Each station does one job, and by keeping all the stations busy at once, you finish more items per hour, even though each item still takes the same amount of time at each station. This means a pipelined CPU can, under ideal conditions, complete roughly 1 instruction per clock tick, even though each instruction takes multiple ticks to travel through the full pipeline. In practice, it's messier than that, because sometimes the pipeline stalls when one instruction depends on the result of another, or when the CPU guesses wrong about which instruction to fetch next. But the basic principle holds. Overlap the stages, keep the pipeline full, and you get much more work done per second. The registers I keep mentioning deserve a closer look. A register is the smallest and fastest kind of storage in the entire computer. Each one holds a single value, a number made up of some fixed number of bits. A typical CPU has only a small handful of registers, maybe a few dozen. That's not very many, but because registers are built right into the CPU, physically part of the same chip, reading from or writing to a register is almost instantaneous. When the ALU needs to add two numbers, it reads them from registers, adds them, and writes the result back to a register. All of that happens in the time of one or a few clock ticks. This is very different from reading data out of the computer's main memory, which is a separate chip connected to the CPU by a pathway called a bus. Getting data from main memory takes much longer, relatively speaking. And this speed gap turns out to be one of the most important constraints in all of computer design. But that's a topic for the next section. There's one more idea I want to show you here, and it's the idea that makes a computer rather than just a fast calculator. It has to do with where the instructions come from. In the architecture that nearly every modern computer follows, the instructions and the data live in the same memory. The CPU fetches instructions from memory the same way it fetches data from memory, through the same bus, from the same storage. This is called the von Neumann architecture, after the mathematician John von Neumann, who described it in a document written in 1945. The idea seems obvious now, but it wasn't always. Before the stored program concept, computers were wired for one specific task. The most dramatic example is ENIAC, which was completed in 1945 at the University of Pennsylvania. ENIAC was among the earliest electronic general-purpose computers. It used about 18,000 vacuum tubes and weighed roughly 30 tons. It could be configured to solve different types of problems, which made it general purpose. But the configuration itself was physical. To change what ENIAC calculated, a team of operators, often women mathematicians who rarely received public credit at the time, had to manually rearrange cables and set switches across the machine's panels. This process could take days. The machine could compute at electronic speed, but reprogramming it was a mechanical, hands-on job. The stored program concept, described by von Neumann in his first draft of a report on the EDVAC in that same year, 1945, solved this by putting the instructions in the same memory as the data. The insight was simple, but transformative. If instructions are just binary numbers, and memory stores binary numbers, then instructions can live in memory alongside everything else. Now, to change what the computer does, you don't rewire anything. You just load a different set of instructions into memory. The CPU doesn't know or care whether the binary values it's fetching are instructions for a word processor, a game, or a web browser. It just reads the next value from the address in its program counter, decodes it, and does what it says. The flexibility of every modern computer, the fact that the same machine can browse the web, play music, edit a spreadsheet, and run a weather simulation, comes directly from this one architectural decision. The hardware stays the same, only the instructions change. Von Neumann's architecture has a trade-off though, because instructions and data share the same memory and the same bus. The CPU can only do one thing at a time on that bus. It can fetch an instruction, or it can load a piece of data, but not both simultaneously. This limitation is called the von Neumann bottleneck, and it means that the speed of the bus, the rate at which data can travel between the CPU and memory, puts a ceiling on how fast the whole system can work. A great deal of modern computer design, from caching to pipelining to the memory hierarchies we'll talk about next, exists specifically to work around this bottleneck without abandoning the elegance of the original architecture. We're about halfway down now. The electrons are doing real work. You've seen the switches, the gates, the adder, the instruction cycle, and the stored program concept that makes a general-purpose computer possible. But we still haven't reached the bottom of the stack, and the trip back up through the software layers is where the picture really comes together. Before we head that direction, though, there's a question that the CPU keeps bumping into every single time it tries to fetch an instruction or load a piece of data. Where does it go to get these things? We've been saying memory, but what does that actually mean? It turns out there isn't just one kind of memory. There are several, arranged in a careful hierarchy, from very fast and very small to very slow and very large. And the reason for that hierarchy is one of the most practical constraints in all of computing. The constraint is simple, and it comes straight from physics. The fastest memory you can build is also the most expensive, and you can't fit very much of it in one place. The cheapest memory, the kind you can buy in large quantities, is slow. There is no technology that gives you fast, large, and cheap all at once. So every computer ever designed solves this the same way. It uses several different kinds of memory, arranged in layers, with the fastest and smallest closest to the CPU, and the slowest and largest farthest away. This arrangement is called the memory hierarchy, and understanding it explains why your computer feels fast, even though most of its storage is, relatively speaking, quite slow. Let's start at the top of the hierarchy, with the memory we already met in the last section. Registers are the fastest storage in the entire machine. They're built right into the CPU chip, physically part of the same piece of silicon as the ALU and the control unit. A register holds a single value, one number made up of a fixed number of bits. A typical CPU has only a few dozen of them. That's not a lot of space. But because they're so close to the circuits that use them, reading from or writing to a register takes almost no time at all. When the ALU adds two numbers, it pulls them from registers and writes the result back to a register. And the whole thing happens within the span of a few clock ticks. Registers are where the CPU does its thinking, if you can call it that. They're the workbench, the surface where the current job is spread out. But a few dozen values is nowhere near enough to hold everything a program needs. Even a simple program might work with thousands or millions of data points. So the next layer down is cache. Cache is also built into the CPU chip, but there's more of it than there are registers, and it's slightly slower. Most modern processors actually have several levels of cache, commonly called L1, L2, and L3. L1 is the smallest and fastest, sitting right next to the processing cores. L2 is larger and a little slower. L3 is larger still and shared across multiple cores. The point of cache is to keep a copy of data that the CPU has used recently or is likely to use soon, so that when the CPU needs it again, it doesn't have to go all the way to main memory to get it. This works because of a pattern called locality. Programs tend to access the same data repeatedly, or to access data that's stored near other data they've recently used. If you're reading through a document, for example, the next piece of data you need is probably stored right next to the piece you just read. Cache exploits this pattern. When the CPU asks for a value, the cache checks whether it already has a copy. If it does, that's called a hit. and the data comes back almost immediately. If the cache doesn't have a copy, the request has to travel down to the next level of the hierarchy, which takes considerably longer. A well-designed cache hits most of the time, which is why your computer doesn't feel slow, even though its main memory is many times slower than its registers. Below cache sits main memory, which most people call RAM, short for random access memory. RAM is a separate set of chips on the motherboard, connected to the CPU by a bus. It's much larger than cache, large enough to hold the data and instructions for all the programs you currently have open. But it's also much slower than cache, because the data has to travel across that bus, and the bus is a shared resource that can only carry so much at a time. This is part of the von Neumann bottleneck we talked about in the last section. The CPU can process data far faster than the bus can deliver it, so the cache exists to bridge that gap, feeding the CPU from its own fast local copy whenever possible. RAM has another important property, and it's one that surprises people when they first learn about it. RAM is volatile. That means it only holds data as long as the computer is powered on. The moment you shut down, or the power flickers, or the battery dies, everything in RAM disappears, gone, not corrupted, not hidden somewhere, just gone. The chips need a constant supply of electricity to maintain the charges that represent your data. Cut the power, and the charges drain away in a fraction of a second. This is why you have to save your work. The act of saving moves data from RAM, where it's fast but temporary, down to the next layer, persistent storage. And it's why a sudden power outage can cost you whatever you hadn't saved. The data was real. It was sitting right there in memory, but it only existed as long as the electricity held it in place. Persistent storage is your hard drive or solid-state drive. This is where your files live when you're not using them. Your documents, your photos, your music, the applications you've installed, the operating system itself, all of it sits on persistent storage, waiting to be loaded into RAM when you need it. Storage keeps your data even when the power is off. A solid-state drive stores bits by trapping electrons in tiny cells, and those electrons stay trapped for years without any power. An older spinning hard drive stores bits as tiny magnetic patterns on a rotating metal platter, and those patterns persist just as reliably. This is the fundamental trade-off of persistent storage. It holds things permanently, but reading from it is the slowest operation in the hierarchy by a wide margin. Persistent storage is also vastly larger than RAM. A typical computer might have thousands of times more storage space than it has RAM. Reading data from a solid-state drive is many times slower than reading from RAM, and reading from an older spinning hard drive is slower still. The trade-off is clear. Storage is big and permanent, but you pay for that with speed. So the hierarchy, from top to bottom, goes registers, cache, RAM, storage. Each layer is larger, cheaper per bit, and slower than the one above it. The system works because the layers cooperate. When the CPU needs a piece of data, it checks the registers first, then the cache, then RAM, and only goes to storage as a last resort. And when data comes up from a lower layer, a copy usually gets stored in the higher layers, so that the next time it's needed, the access is faster. The whole system is designed around the assumption that most of the data the CPU needs at any given moment is data it has used recently, or data that's nearby in memory. And most of the time, that assumption is correct. Let's trace this hierarchy with the example we've been following since the beginning. When you click that link and your browser asked for a web page, the HTML file was sitting on a server somewhere, stored on that server's persistent storage. A program on the server read the file from storage into the server's RAM, then sent it across the network. When the data arrived at your computer, it went into your computer's RAM. When the browser started to parse the HTML, the CPU needed to read it, so the relevant sections got pulled from RAM into the cache. And when the CPU actually executed the instructions that parsed each piece of the document, the data it was working with sat in registers, right there on the chip, available in a fraction of a tick. The file made the entire journey, from a hard drive on the other side of the world to a register inside your processor, passing through every layer of the hierarchy along the way. Each transition traded size and permanence for speed, getting the data closer and closer to the one place where actual work happens. The reason I'm spending time on this is that the memory hierarchy explains something that might have seemed like magic earlier. How can a computer feel instant when the data it needs might be stored on a device that takes comparatively ages to read? The answer is that most of the time, the data the CPU needs is already in cache. The cache is doing quiet, invisible work in the background, guessing what the CPU will want next and having it ready. When the guess is right, which is most of the time, the CPU never has to wait. When the guess is wrong, you feel it. That tiny stutter when a program takes a moment to open, or when a file takes an extra beat to load, that's often a cache miss rippling down through the hierarchy, the CPU idling while it waits for data to arrive from a slower layer. But something might occur to you if you've been following the trail of who does what inside this machine. We've talked about the CPU fetching instructions and executing them. We've talked about data moving up and down the memory hierarchy. But who decides which data goes where? Who loads the right file from storage into RAM? Who manages the cache? Who keeps track of all the programs running at the same time and makes sure they don't overwrite each other's data? The CPU just follows instructions. The memory just stores values. Neither of them is in charge. Something has to be organizing all of this, directing traffic, managing resources, making sure the right program gets the right data at the right time. And that something is software. The question that pulls us into the next layer is, where does that software come from? And how do human-readable instructions become the binary patterns that the CPU understands? Software starts as something you could read. Not comfortably, maybe. Not the way you'd read a novel. But you could open the file, look at the words, and get a rough sense of what it's telling the computer to do. That file is called source code, and it's written in a programming language. There are hundreds of programming languages, but they all share the same basic purpose. They let a human being describe a sequence of operations in a way that's structured enough for a machine to follow, but readable enough for a person to write and understand. A programming language like C might have a line that says something like, result equals first value plus second value. It's not plain English. There are rules about syntax and punctuation, but the intent is clear. You're telling the machine to add two things and store the answer. A language like Python might express the same idea in an even simpler way, with fewer symbols and less ceremony. JavaScript, the language that runs inside your web browser and powers most of the interactive behavior on web pages, has its own style, its own rules, its own way of expressing the same kinds of operations. But none of these languages can be run directly by the CPU. The CPU doesn't understand Python. It doesn't understand C. It doesn't understand any human-readable language at all. The CPU only understands machine code, which is a sequence of binary numbers, each one encoding a specific operation. Add these two registers, load this value from memory, compare these two numbers, and jump to a different instruction if they're equal. Machine code is not meant to be read by people. It's the native language of the hardware. So there has to be a translation step. Something has to take the human-readable source code and turn it into the binary instructions the CPU can execute. This is one of the central ideas of the whole field, and it's worth sitting with for a moment. The source code is for you. The machine code is for the chip. They describe the same computation, but in completely different languages, at completely different levels of detail. The source code says what to do. The machine code says exactly how to do it, down to which registers to use, which memory addresses to access, and which specific binary operation to perform at each step. Bridging that gap is the job of translation software, and how that translation happens depends on the language. For some languages, the translation is done all at once, before the program ever runs. This is called compilation. A compiler is itself a program, a piece of software that reads an entire source code file, analyzes its structure, and generates a corresponding file of machine code. That machine code file is what actually runs on your computer. When you install an application, what you're often installing is the already compiled machine code, not the original source code. The programmer wrote the source, compiled it, and shipped the result. This is how languages like C and its relatives work. One important consequence of compilation is that machine code is specific to a particular type of CPU. Different processors have different instruction sets, different binary patterns that mean different things. So the same C source code has to be compiled separately for each type of processor it needs to run on. The source code is universal. The compiled result is not. Other languages take a different approach. Instead of translating the entire program in advance, they use something called an interpreter. An interpreter is a program that reads the source code and carries out the instructions more or less as it encounters them, translating and executing in a tighter loop, rather than producing a separate machine code file. Python is often described this way. You write a Python script, and when you run it, the Python interpreter reads your code and executes it. The distinction between compilation and interpretation is real, but in practice, the line is blurrier than it sounds. Many modern interpreters actually compile portions of the code internally, translating frequently used sections into machine code on the fly to speed things up. JavaScript engines in modern browsers do this aggressively, using a technique called just-in-time compilation. The browser's JavaScript engine starts by interpreting the code, but when it notices a section that runs repeatedly, it compiles that section into optimized machine code so it runs faster the next time. So calling JavaScript purely interpreted would be an oversimplification. The truth is more of a spectrum, with pure compilation on one end, pure interpretation on the other, and most modern languages sitting somewhere in between. There's a layer between human-readable languages and raw binary that's worth pausing on, because it reveals how the translation actually works. It's called assembly language, and it's a fascinating thing to look at if you've never encountered it before. Assembly is about as close to the hardware as you can get while still using words instead of numbers. It's not pleasant to read in large quantities, and writing a complex program in assembly is an exercise in patience that most modern programmers rarely have to attempt. But it's wonderfully transparent. There's almost nothing hidden. Each line of assembly corresponds closely to a single machine instruction. A line might say something like, add register 1, register 2, register 3, meaning take the values in the first 2 registers, add them, and put the result in the third. Another line might say, load register 4, memory address, meaning go to that location in memory and copy the value into register 4. The words are shorthand, but the structure mirrors the binary instruction almost exactly. When a compiler translates a high-level language like C into machine code, assembly language is often an intermediate step. The compiler first generates assembly, and then a simpler program called an assembler converts the assembly into the actual binary numbers the CPU reads. The set of instructions that a particular CPU understands is called its instruction set. You can think of the instruction set as the chip's vocabulary, the complete list of operations it knows how to perform. Some instruction sets have relatively few instructions, each one doing a simple, focused task. Others have hundreds of instructions, including specialized ones for things like multimedia processing or encryption. Different families of processors have different instruction sets. The processor in a desktop computer might use a different instruction set than the processor in a phone, which means machine code compiled for one won't run on the other, at least not without a translation layer. This is one of the reasons why the source code matters so much. The source code is portable. It describes what you want the computer to do in abstract terms. The machine code is specific, tied to a particular chip's instruction set. The compiler is the bridge between the two, and it's the compiler's job to know the details of the target chip, so the programmer doesn't have to. The programmer writes the logic once, and the compiler figures out how to express that logic in whatever instruction set the target machine speaks. If you step back and look at the whole picture, what you see is a stack of translations, one layer of language sitting on top of another. At the very top is the programmer, a person thinking in terms of problems and solutions, writing in a language designed for human understanding. Below that is the compiler or interpreter, which translates the human-level description into something closer to the machine's level. Assembly sits in between, a thin, readable veneer over the binary, close enough to the hardware that you can see the individual instructions but still using words you can recognize. And at the bottom is machine code, the actual sequence of binary numbers that the CPU fetches, decodes, and executes one at a time, using the cycle we walked through 2 sections ago. The distance between the top and the bottom of this stack is enormous. A single line of Python might translate into dozens or hundreds of machine instructions. A complex program might contain millions of lines of source code, compiling down to billions of machine instructions. Every app on your phone, every game, every browser, every operating system was written as source code by a human being, and then translated, step by step, down to the patterns of ones and zeros that the hardware can act on. The high-level code exists entirely for the programmer's benefit. The CPU has never seen it, and never will. And that word abstraction keeps coming back, because it's really the central theme of this entire journey. This is the same pattern we've been seeing at every layer. Each level of the machine exists to hide the complexity of the level below it. The programmer doesn't need to think about registers and instruction sets, because the language and the compiler handle that. The compiler doesn't need to think about transistors and voltage thresholds, because the digital abstraction handles that. Each layer trusts the one below it, speaks its own language, and never looks deeper than it has to. But now there's a puzzle, and it's one of those puzzles that seems like it shouldn't have a solution until you see how it's actually solved. We've been talking about software, source code, compilers, interpreters, machine instructions. All of this assumes that there's already a program running. The compiler is a program. The interpreter is a program. The operating system that manages everything is a program. But when you first turn on your computer, before the operating system has loaded, before any software is running at all, the CPU is just sitting there, freshly powered, with nothing in its registers and no instructions in its pipeline. The memory might be full of random leftover voltages from the last time the machine was on. How does the very first program get loaded? How does a machine that needs software to do anything manage to start its first piece of software from nothing? The answer is a trick, and once you see it, you realize it's the only trick that could possibly work. The CPU is designed so that the very first thing it does when power arrives is start executing instructions from a specific, predetermined location. The designers of the chip decide that location when they build it. It's fixed, hardwired into the processor. Every time the chip powers on, the program counter gets set to that address, and the CPU immediately begins that same cycle from there. It doesn't check whether there's anything useful at that address. It doesn't wait for a signal. It just starts reading and executing whatever binary values it finds. So the question becomes, what's at that address? The answer is firmware, a small program stored on a dedicated chip on the motherboard, separate from the main memory. This chip holds its data permanently, even when the power is off, because it uses a type of storage that doesn't need electricity to retain its contents. When the CPU powers on and reaches for that fixed starting address, the hardware routes the request to this chip, and the firmware's instructions begin to execute. On most personal computers, the firmware is either something called BIOS, which stands for Basic Input-Output System, or its more modern successor, called UEFI, which stands for Unified Extensible Firmware Interface. BIOS has been around since the earliest IBM personal computers in the early 1980s. UEFI is a more recent standard that offers more features, including the ability to handle larger storage devices and a more flexible boot process. The details differ between the two, and different manufacturers implement them in slightly different ways, but the basic role is the same. The firmware's job is to get the machine from just powered on to ready to load an operating system. It does this in stages, and the whole process happens so quickly that you barely notice it. That brief pause between pressing the power button and seeing anything on the screen. That's the firmware working. The first thing the firmware typically does is check the hardware. It needs to verify that the essential components are present and functioning Is there a CPU? Is there memory? Is the display connected? Are the storage devices responding? On many systems, this initial check has traditionally been called a power-on self-test, though the specifics of what gets tested and how vary across manufacturers and firmware versions. If something critical is missing or broken, the firmware signals an error, sometimes with beep codes through a small speaker, sometimes with blinking lights, sometimes with a message on the screen if the display is available. If the essential hardware passes, the firmware moves on. The next step is to find a boot device. The firmware knows how to talk to storage devices at a very basic level, just enough to read a specific location on a hard drive, a solid-state drive, or a USB device. It looks through a list of devices in a priority order, the boot order, and checks each one for a bootloader. The bootloader is a small program stored in a known location on the device, and its existence at that location is what tells the firmware that this device contains an operating system. When the firmware finds a bootloader, it loads it into main memory and hands control over to it. The firmware's job is now done. The bootloader is the second link in the chain. It's a more capable program than the firmware, but still small and focused. Its job is to find the operating system's kernel, load it into memory, and start it running. The bootloader understands just enough about file systems to find its way around the disk and find what it's looking for. On a Linux system, a common bootloader is called grub. Grub can read the file system on the disk, find the kernel file, which is usually a compressed binary sitting in a specific directory, and decompress it into memory. If you have multiple operating systems installed on the same machine, the bootloader is typically the program that lets you choose which one to start. It presents a menu, you pick an option, and it loads the corresponding kernel. On Windows, a different bootloader performs the same role. On a Mac, the process is similar in concept, but handled by Apple's own firmware and boot system. The details change, but the structure is the same. A small, focused program that loads a larger, more capable program. Now the kernel takes over, and the machine really starts to become a computer in the sense you'd recognize. The kernel is the core of the operating system. If you think of the operating system as a government, the kernel is the executive branch. It makes the fundamental decisions about how resources get allocated, who gets access to what, and how conflicts are resolved. It's the first real software to run, the program that will manage everything else from this point forward. But when it first starts executing, the machine is still in a very raw state. The kernel can't assume anything has been set up for it beyond what the bootloader provided. It starts, essentially, from scratch. The kernel's first tasks are fundamental setup work. It initializes the memory management system, which means it takes stock of how much RAM is available and sets up the structures it needs to allocate memory to future programs. It detects and initializes hardware, the processor, the storage controllers, the network interfaces, the display. For each piece of hardware, it loads a driver, a small piece of code that knows how to communicate with that specific device. On a Linux system, there's an interesting intermediate step that happens between the bootloader handing off to the kernel and the kernel having full access to the main file system. On disk, the kernel often starts with a temporary file system loaded entirely into RAM, called an initial RAM file system. This temporary file system contains just enough tools and drivers for the kernel to find and mount the real root file system on the actual storage device. Once the root file system is mounted, the temporary one is no longer needed and gets discarded. This extra step exists because the kernel might need specific drivers to access the disk where the real file system lives, and those drivers might themselves be stored on that same disk. The initial RAM file system breaks this circular dependency by providing those critical drivers from a separate source. Once the root file system is mounted and the kernel has access to the full set of files on disk, it launches the init system. On most modern Linux distributions, this is a program called systemd, though other init systems exist. The init system is the first ordinary user space program to run, and its job is to start all the services and programs that make up the rest of the operating system. It works through a list of dependencies. This service needs the network to be ready, so start the network first. This service needs the display server, so start the display server first, and so on, methodically, until everything is running. The networking service starts, so the computer can connect to the internet. The display server starts, so graphics can be drawn on the screen. The login manager starts, so you see a prompt to enter your password. Sound services start, so the computer can play audio. A clock service synchronizes the system time. Background update checkers start looking for new software versions. By the time you see your desktop and your icons and your wallpaper, dozens of programs are already running in the background, each one started by the init system in the right order, and most of them will keep running silently for as long as the computer is on. The whole process is a chain. Firmware loads the bootloader. The bootloader loads the kernel. The kernel sets up the hardware and loads the init system. The init system launches everything else. Each link in the chain is a small program whose only real job is to load and start the next, slightly larger program. The name for this process, bootstrapping, comes from the old expression, pulling yourself up by your bootstraps, which describes something impossible. And in a sense, it is impossible. A machine that needs software to function can't load its own software. The trick is that the very first program was placed there by the hardware designers, burned into a chip, waiting at a fixed address for the CPU to come looking. The chain begins with hardware and ends with software. And every modern computer, every phone, every tablet, every server follows some version of this same chain every time it powers on. The specifics vary. The firmware is different. The bootloader is different. The init system is different. But the shape is always the same. A fixed starting point in hardware. A series of ever larger programs, each one handing off to the next. If you've been enjoying this slow walk through the machine and you want to follow the rest of the journey back up to your web page, subscribing is the easiest way to keep it in your feed. The operating system is now running. The kernel is managing the hardware. The init system has launched the services. Your desktop is on the screen. But here's something that might seem strange if you think about it. You're about to open a web browser, a music player, a text editor, maybe a few other programs. Your computer has one CPU, or at most a handful of cores. How does it run all of those programs at the same time? How does one processor, executing one instruction at a time through that same instruction cycle we walked through earlier, manage to keep dozens of programs running without any of them stepping on each other? The short answer is that the operating system cheats, and cheats so convincingly that no program ever notices. The longer answer involves one of the cleverest tricks in all of computing, and it starts with a concept called a process. When you open a program, the operating system creates a process for it. A process is the operating system's way of keeping track of a running program, what code it's executing, what data it's working with, which registers it's using, where it is in its instruction sequence, and what resources it has been given. Every open program is a process. Your web browser is a process. Your text editor is a process. The music player running in the background is a process. Each one believes, because the operating system has gone to great lengths to make it believe that it has the entire machine to itself. The operating system maintains this illusion through scheduling. The kernel contains a component called the scheduler, and the scheduler's job is to decide which process gets to run on which CPU core and for how long. Modern processors usually have multiple cores, which means several processes can genuinely run at the same time, one per core. But you typically have far more processes running than you have cores. A computer with 4 or 8 cores might have dozens or even hundreds of active processes. So the scheduler gives each process a small slice of time on a core, usually just a few milliseconds, and then pauses it and gives the next process its turn. This rotation happens so quickly that every process appears to run continuously. The music doesn't stutter. The browser doesn't freeze while you type in the text editor. From the user's perspective, everything runs at once. From the CPU's perspective, each core is rapidly switching between tasks, one at a time, The act of switching from one process to another is called a context switch, and it's one of the most carefully optimized operations in any operating system. When the scheduler decides it's time to pause one process and start another, the kernel has to save everything about the current process's state, the values in the CPU's registers, the position of the program counter, the flags, everything the CPU was working with. All of that gets stored in a data structure associated with that process. Then the kernel loads the saved state of the next process into the CPU's registers, sets the program counter to where that process left off, and lets the CPU resume. From the process's point of view, nothing happened. It was running, and then it's running again. It has no idea that in between, the CPU spent a few milliseconds doing something else entirely. But sharing the CPU's time is only half the problem. The harder half is sharing memory. If 2 programs are running on the same machine, and they can both read and write to the same memory, chaos follows. One program could accidentally overwrite another program's data, or worse, intentionally read sensitive information from another program's memory. The operating system prevents this through virtual memory and memory protection. Here's how it works. Each process gets its own virtual address space, which is the process's personal view of memory. When a process refers to a memory address, it's using a virtual address, not a physical one. The operating system, with help from a hardware component in the CPU called the Memory Management Unit, translates each virtual address into an actual physical address in RAM. 2 different processes can use the same virtual address, and the hardware will map them to completely different locations in physical memory. Process A's address, 1000, might point to one physical location, and process B's address, 1000, might point to a completely different one. Neither process can see or touch the other's memory, because they don't even know the other's physical addresses exist. The memory management unit divides memory into small, fixed-size chunks called pages. A typical page might be a few thousand bytes. The operating system keeps a table for each process, the page table, that maps each virtual page to a physical page in RAM. When a process accesses memory, the hardware looks up the mapping in the page table and routes the request to the right physical location. If a process tries to access a page it doesn't own, the hardware raises an exception, and the operating system steps in, usually by terminating the offending process. This is what happens when a program crashes with an error about accessing invalid memory. The memory protection hardware caught it. This system also enables a trick we touched on briefly in the memory section, and now we can see exactly how it works. If RAM starts to fill up, the operating system can take pages that haven't been used recently and write them out to the persistent storage device, freeing up physical RAM for other things. This is called swapping or paging. It's a clever way to stretch a limited resource, because the operating system is betting that most pages sitting idle in RAM won't be needed again for a while. And if they are, it can bring them back. When the process that owns those pages tries to access them again, the hardware raises a page fault. The operating system retrieves the pages from storage back into RAM, updates the page table, and lets the process continue. The process never knows this happened. As far as it's concerned, the data was in memory the whole time. Virtual memory means that processes can collectively use more memory than the machine physically has, at the cost of speed when swapped pages need to be retrieved. There's an important boundary between what a regular process can do and what the operating system kernel can do, and the CPU hardware enforces it. The processor operates in at least two privilege levels, often called user mode and kernel mode. Regular programs run in user mode, where certain operations are restricted. A program running in user mode cannot directly access hardware, cannot modify the page tables, cannot interact with other processes' memory, and cannot execute certain privileged instructions. When a program needs to do something that requires higher privilege, like reading a file from disk, sending data over the network, or allocating more memory, it makes a system call. A system call is a controlled doorway into the kernel. The program asks the kernel to perform the operation on its behalf. The CPU switches to kernel mode. The kernel does the work, and then control returns to the program in user mode. This boundary is what keeps one misbehaving program from bringing down the entire machine. Below the kernel, sitting between the operating system and the physical hardware, are the device drivers. A driver is a small piece of code that knows how to talk to one specific piece of hardware. There's a driver for your network card, a driver for your display, a driver for your storage controller, a driver for your keyboard, and so on. The kernel communicates with hardware through these drivers, using a standardized interface, so that the rest of the operating system doesn't need to know the specific details of each device. When your browser wants to send a message over the network, it asks the operating system. The operating system passes the request to the network driver. The network driver translates the request into the specific electrical signals that the network card understands. The hardware does the actual sending. This layering means that the browser doesn't know or care what brand of network card you have, and the network card doesn't know or care what the browser is trying to do. They communicate through the operating system, and the operating system handles the translation. The file system works on a similar principle. The raw storage device, your hard drive or solid-state drive, is just a vast expanse of numbered blocks. Each block holds a fixed number of bytes. There's no inherent structure, no files, no folders, just blocks. The file system is the layer of software that imposes structure on this raw space. It maintains tables that map file names to block locations, track which blocks are free, record permissions and timestamps, and organize everything into the directory hierarchy you see when you open a file manager. When you save a document, the file system finds free blocks, writes your data into them, and updates its tables so it knows where to find the data later. When you open that document again, the file system looks up which blocks it, occupies, and reads them back in order. Different operating systems use different file systems, each with its own way of organizing the tables and managing the blocks. But the basic idea is the same everywhere. The file system takes a flat expanse of numbered storage and gives it the familiar structure of names, folders, and paths that you interact with every day. We're turning around now. From here, every layer we pass through on the way back up exists to hide the one below it, to take something complicated and present it to the layer above as something simple. The operating system hides the raw hardware behind clean interfaces. The network stack, which we'll see next, hides the physical infrastructure of the internet behind the simple act of sending and receiving messages. And the browser, at the very top, hides all of it behind the page you see on your screen. We're heading back toward that web page now, and the next question is the one that takes us outside the machine entirely. Your browser needs to fetch a page from a server that might be thousands of miles away. How does a message leave your computer, cross the physical network, and come back with the right data? Everything we've talked about so far happens inside a sealed box. The transistors, the logic gates, the CPU cycling through its instructions, the memory hierarchy shuttling data up and down, the operating system managing it all. None of that touches the outside world. Your computer is a machine that manipulates voltages on a chip, but you interact with it through a keyboard, a touch screen, a mouse. It shows you things on a display. It plays sound through speakers. And right now, in the story we've been following, it needs to reach across a network and talk to another computer that might be sitting in a building on the other side of the planet. All of that requires input and output, which is the general term for any communication between the computer and anything that isn't the computer. Every device that connects the machine to the outside world is an input/output device. Your keyboard sends signals in. Your display receives signals out. Your network card does both. It sends data out onto the network and receives data back. These devices don't communicate with the CPU directly. They're connected through a bus, which is a shared pathway for data, and the operating system mediates every exchange. When you press a key, the keyboard controller sends an interrupt, a small electrical signal that tells the CPU to pause what it's doing and deal with this new event. The CPU doesn't constantly check whether you've pressed a key. That would be a waste. Instead, the hardware interrupts it only when something actually happens. the CPU pauses its current work, saves just enough state to pick up where it left off, runs a short piece of code called an interrupt handler to process the event, and then resumes what it was doing. This happens so quickly that you never notice, but it's the mechanism underneath every keystroke, every mouse movement, every packet arriving from the network. The outside world doesn't wait politely for the CPU to be ready. It interrupts. The device we care about right now is the network interface. It might be a physical card plugged into the motherboard with an Ethernet cable running out the back, or it might be a wireless radio that communicates with your router through the air. Either way, its job is to convert the data your computer wants to send into signals that can travel over a physical medium, a wire, a radio wave, a beam of light in a fibre optic cable, and to convert incoming signals back into data the computer can use. The network card is the boundary between the digital world inside your machine and the physical world outside it. When your browser decided it needed to fetch a web page, the operating system prepared a message. But before that message can go anywhere, the browser needs to figure out where to send it. You typed or tapped a human-readable name, something like a domain name. But the network doesn't route messages by name. It routes them by numeric address. Every device participating in the network has an IP address, which is just a number that identifies it. Your computer has one, assigned by your local network. The server hosting the web page has one too. To find the server's address, your browser uses the domain name system, or DNS. DNS works a bit like a chain of directories. Your computer first checks its own memory, because if you visited this site recently, it probably still has the address cached from the last time it asked. If it doesn't find it locally, it asks a DNS resolver, usually one provided by your internet service provider. That resolver might have the answer cached from someone else's recent request for the same name. If not, it starts asking a series of authoritative name servers, each one responsible for a piece of the namespace, until it gets back the specific IP address associated with that domain name. The whole process usually takes fractions of a second, and once your browser has the address, it caches the result, so it won't have to repeat the chain of lookups for a while. This is one of those layers of indirection that you never see and rarely think about. You type a name, and behind the scenes, a small flurry of queries and responses translates it into the number the network actually needs. Now your browser has an address. It knows where to send its request, but sending data across the internet isn't as simple as just pointing a message at a destination. The data has to be broken into smaller pieces because the network can't carry one giant stream. It carries individual packets, each one a small, self-contained bundle of data with a header that says where it came from and where it's going. This is where the Internet Protocol comes in. IP is the addressing and routing layer. It handles getting each packet from your machine to the destination machine. Every packet carries the source IP address and the destination IP address. And as it travels through the network, each router it encounters reads the destination address and decides which direction to forward it. Different packets heading to the same destination might take different paths through the network, depending on conditions at the time. There's no single fixed route. Each router makes a local decision based on its own routing tables, and the packets find their way. But IP alone doesn't guarantee that the packets arrive, or that they arrive in order, or that none of them get lost along the way. IP is a best effort system. It sends packets and hopes they get there. For a web page, hope isn't enough. You need the complete data, in the right order, with nothing missing. That's what the Transmission Control Protocol provides. TCP sits on top of IP and adds reliability. Before any data flows, TCP establishes a connection between your computer and the server through a three-step process. Your machine sends a synchronization signal. The server responds with its own synchronization signal and an acknowledgement, and your machine sends a final acknowledgement back. This is called the three-way handshake, and it's described in the original TCP specification published in 1981. Once the connection is established, TCP numbers every piece of data, tracks which pieces have been received, detects missing or corrupted pieces, and requests retransmission when needed. It also manages flow control, adjusting how fast data is sent so that neither end gets overwhelmed. By the time the data reaches your browser, TCP has assembled it into the correct order and verified its completeness. The browser never has to worry about missing packets. TCP handled that. There's one more handshake before the actual web page data starts flowing, and it's one you benefit from every time you see a padlock icon in your browser's address bar. Most websites today use HTTPS, which wraps the HTTP communication inside a layer called TLS, or Transport Layer Security. After the TCP connection is established, but before any web page content is exchanged, your browser and the server perform a TLS handshake. During this process, the server proves its identity with a certificate, and the two sides agree on encryption keys. From that point forward, everything sent between your browser and the server is encrypted. Someone watching the data pass through the network can see that packets are flowing between your machine and the server, but they can't read the contents. This adds a small amount of time to the connection setup, but it's the reason your banking information, your passwords, and the contents of the page you're loading remain private as they cross the open network. Now the secure connection is open, and your browser sends its request. This is an HTTP request, and it's simple. It's a message that says, I want this specific resource at this specific address. The server receives the request, finds the resource, which in our case is an HTML file that describes the structure of a web page, and sends it back as an HTTP response. The response includes the HTML itself, along with some metadata: how large it is, what type of content it is, whether the browser is allowed to cache it. But where does this request physically go? Your network card converts the data into electrical signals or radio waves. Those signals reach your router, the small box that connects your home network to the wider internet. The router forwards them to your internet service provider's network. From there, the packets travel through a series of routers and switches, each one reading the destination address and forwarding the packet closer to its target. The physical path might involve copper wire, fibre optic cable, or radio links. If the server is on another continent, the data might travel through undersea fibre optic cables that run along the ocean floor, thin strands of glass carrying pulses of light at enormous speed. The return trip follows the same general principle, but not necessarily the same exact path. Each router makes its own forwarding decision independently. What matters is that the packets reach the destination and the responses come back. The round trip happens quickly, but not instantly. The data is moving at the speed of light through the fibre. But there are delays at every router, every switch, every point where the signal is received, processed, and forwarded. These delays add up, and the total time for a round trip depends on the distance, the number of hops, and the congestion on the network at that moment. But for most requests to most servers, the entire exchange, DNS lookup, TCP handshake, TLS handshake, HTTP request and response, takes a small enough fraction of a second that you barely notice the gap between tapping a link and seeing the page begin to appear. And now the data has arrived. The HTML sits in your computer's memory, received through the network card, reassembled by TCP, decrypted by TLS, and handed to your browser. It's a text file, nothing more. Characters arranged according to a set of rules that describe headings, paragraphs, links, images, colors, and layout. The browser has it, but a text file isn't a web page. You can't look at raw HTML and see the page the way it's supposed to appear. Something has to read that text, understand its structure, calculate where every element belongs on the screen, and paint the final image pixel by pixel. That final translation, from text to the visual page you actually see, is where we're going next. The browser has the HTML. It's sitting in memory as a sequence of characters, just text, no different in form from any other text file than the computer has ever handled. But this particular text follows a very specific set of rules. It's organized into elements, each one marked by tags that describe what it is. A heading, a paragraph, a link, an image, a list. The browser's first job is to read that text and understand its structure. And it does this through a process called parsing. Parsing begins with tokenization. The browser reads through the HTML character by character and identifies each meaningful piece. The opening of a tag, the name of that tag, any attributes it carries, the text content between tags, the closing tag. These pieces are called tokens, and they're the raw building blocks. As the browser produces tokens, it assembles them into a tree structure called the Document Object Model, or DOM. The DOM is the browser's internal representation of the page's structure. Each element in the HTML becomes a node in the tree. A heading is a node. A paragraph inside a section is a child node of that section. A link inside a paragraph is a child of the paragraph. The tree mirrors the nesting of the HTML, and by the time the browser has finished parsing, it has a complete map of every element on the page and how they relate to each other. But structure alone doesn't tell the browser what anything should look like. A heading node in the DOM says, "This is a heading," but it doesn't say what font to use, how large the text should be, what color, how much space to leave above and below it. That information comes from style sheets, written in a language called CSS. The browser parses the CSS the same way it parsed the HTML, reading through the rules and building a second tree-like structure that describes the visual properties of each element. MDN calls this the CSS object model, or CSSOM. Some styles come from the page's own style sheet. Some come from the browser's built-in defaults. Some might come from your own browser settings. If you've changed things like the default font size, the browser gathers all of these sources and resolves them into a single set of computed styles for every element, following a specific hierarchy of priority when rules conflict. Now the browser has two structures: the DOM, which describes what's on the page, and the CSSOM, which describes how each element should look. The next step is to combine them. The browser walks through the DOM and, for each node, looks up its computed styles. It skips elements that are explicitly hidden, elements whose styles say they should not be displayed. Everything that remains gets assembled into what is sometimes called a render tree, though different browser engines use different terminology for this internal structure. What matters is the result: a tree of only the visible elements, each one carrying its full set of visual properties. This is the data structure that the rest of the rendering pipeline will work from. With the render tree built, the browser moves into layout. Layout is pure geometry. The browser has to calculate the exact position and size of every visible element on the screen. It starts from the top of the page and works downward, determining how wide each element is based on the width of its container and its own style rules, how tall it is based on its content and padding and borders, and where it sits relative to its siblings and its parent. Text wraps according to the available width. Images take up the space their dimensions require. Elements that are set to float or to position themselves in special ways get placed according to those rules. If the page contains tables, the browser has to figure out how wide each column should be based on its contents and constraints before it can place the cells. The output of layout is a precise geometric map. Every element has coordinates, a width, and a height, measured in actual screen units. If you've ever resized a browser window and watched the text reflow and the elements shift, that's the layout engine recalculating the geometry in response to the new dimensions. After layout comes paint. The browser now fills in the visual content. Text gets rasterized, which means the browser takes the mathematical outlines of each letter in the chosen font and converts them into a grid of colored pixels at the right size. Images that were downloaded alongside the HTML get decoded from their compressed format and placed at the coordinates layout calculated. Backgrounds get filled with their specified colors or gradients. Borders get drawn. Shadows get rendered. Everything that you would eventually see on the screen gets turned into pixel data during this step. The browser doesn't necessarily paint the entire page at once. It divides the page into regions and can repaint individual regions when something changes, like when you scroll or when an animation updates. There's one more step before the image reaches your screen, and it's one that modern browsers have gotten very good at. It's called compositing. The browser may have divided the page into multiple layers during the paint step, because some elements behave independently from the rest of the page. A scrolling region, for instance, moves its content without affecting the elements around it. An animation might update dozens of times per second without needing to repaint the static content behind it. The browser keeps these on separate layers and composites them together, blending them in the correct order, front to back, into a single final image. On most modern systems, this compositing work gets handed to the GPU, the graphics processing unit, which is a specialized processor designed specifically for this kind of parallel visual computation. The GPU is extremely efficient at operations like blending layers, applying transformations, and filling large regions of pixels with color, because it can process many pixels simultaneously, rather than one at a time, the way the CPU handles general instructions. The GPU assembles the final composited image into a buffer of pixel data, and that buffer gets sent to your display. Your screen is a grid of tiny elements, each one capable of producing a specific color. On most modern displays, each pixel is made up of sub-pixels, typically red, green, and blue, though the exact physical arrangement can vary between display technologies and manufacturers. Each sub-pixel glows at a specific brightness, and the combination of those three tiny lights, seen from a normal viewing distance, blends into a single color that your eye perceives as one point of the image. The browser calculated what color each pixel should be. The GPU prepared the data, and now the display is physically producing that color, element by element, across the entire screen, many times per second. The page is there. It's on your screen, right where you expected it to be when you tapped that link. And now you can see what filled that gap. You tapped a link, and your finger changed the electrical field on a touch-sensitive surface. The operating system detected the contact, identified which program owned that region of the screen, and delivered the event to your browser. The browser looked up a domain name, translating a human-readable address into a numeric one through a chain of DNS queries. It opened a TCP connection to a server, handshake by handshake, and wrapped that connection in encryption. It sent an HTTP request across the physical network, through your router, through your internet service provider, through fibre and copper and radio, across routing infrastructure that forwarded each packet independently based on its destination address. A server on the other end received the request, found the file, and sent it back the same way. The data arrived as packets, was reassembled, decrypted, and handed to the browser as text. The browser parsed that text into a tree of elements, matched each one with its visual styles, calculated the geometry of every visible piece, painted the pixels, composited the layers, and sent the final image to the GPU, which lit up the sub-pixels on your display. Every step of that process used binary, because inside this machine, every piece of information is a pattern of voltages representing ones and zeros. Every voltage was controlled by transistors, billions of them, tiny semiconductor switches arranged into logic gates and arithmetic circuits on a chip smaller than your thumbnail. Every operation followed the fetch-decode-execute cycle, the CPU reading one instruction at a time, from memory, decoding it, carrying it out, and moving to the next, billions of times per second. The data traveled up and down a memory hierarchy, from persistent storage to RAM, to cache, to registers and back, each layer trading size for speed. The software that orchestrated all of it, the browser, the operating system, the network stack, the drivers, started as human-readable code, was translated by compilers and interpreters into the binary patterns the hardware understands, and was loaded into memory by a bootstrap chain that began with a tiny program burned into a chip on the motherboard. And every program running on the machine believed it had the whole computer to itself, because the operating system maintained that illusion through scheduling, virtual memory, and protection, layer after layer of abstraction, hiding the one below. That ordinary moment, a tap and a page, is the entire stack working at once. Every layer trusts the one beneath it, and never looks deeper than it has to. The page appears because 80 years of engineering, from vacuum tubes to transistors, to integrated circuits to the software abstractions built on top of them, all converged into a system where each layer does one job and does it well enough that the layers above never need to think about it. The whole machine is an act of hiding complexity so thoroughly that the surface feels simple. And that's the thing worth noticing, if you're still awake to notice it. The simplicity you see on the screen isn't the absence of complexity. It's the result of it.